Hello Minecrafters, and welcome back to another Redstone video. This is episode 5 of learning Redstone computer with Minecraft, and in today's episode we were gonna learn about instruction memory. We were gonna learn about what it is, what does it do, and also how to connect it with our current computer parts. So without any further waiting, let's just jump right into today's episode. First, let's answer our first question, which is, what is an instruction memory? Well, an instruction memory is a memory. Of course, it's a memory, but what it does is it stores instruction, a set of instructions, or in other words, is a memory which stores our program. So basically, the instruction memory allows us to load in and store our program, and the computer can basically access each instruction inside of the instruction memory to execute them. And if you don't remember what instruction is, it's essentially the thing that we have been doing for the past like 3 episodes. So we basically just choose an operation here, and we load into the registers, and then we do some ALU like bitwise logic or like arithmetic operations. So those are instructions, and the instruction memory allow us to basically stores all of those like operation. So we don't have to flick the levers manually here. We can just let the instruction memory stores all of those like operations, all of those lever operations, and we just have to feed a clock signal in order for this part of our computer to like actually execute everything. So what does this instruction memory actually looks like in Minecraft? Well, it looks like this. As you can see, it is pretty big, and this instruction memory can store up to 1024 instructions. The reason why I know that is because there are 10 bits here. So technically we can have 2 to the power of n addresses, and each of those addresses can store one of our instructions. And in Mattbatwings like encoding form, each instruction is a 16 bits of binary string. So each of these like columns that like you are seeing right now, each of these columns is storing an instructions, and there are in total 1024 instructions here that the instruction memory can store. And yes, you can see it's pretty big. A lot of things are in here, but don't worry, it's actually not like super complicated, and I will explain why. So here we have our like address selector as the input for the instruction memory. So each of these redstone torch is like an address, and it's like a decoder. If you remember, a decoder, you can enter a binary code here, and the corresponding redstone torch or the output will turn on. In this case, because we are selecting a bunch of zeros, address 0 is on, so this redstone torch is on, powering this column right here, and this column we're gonna load its instruction into the output of the instruction memory. If you want a more like detailed explanation about this thing, you should really watch Mattbatwings video, but I'm not here to like explain all of this in details. But yeah, the redstone is actually just like that. We have a decoder here which will decode 10 bits into 1024 different outputs, and each of those outputs we were gonna have one of these columns, and each of these columns will store one instruction, and an instruction is a 16 bits long binary string. That's basically an instruction memory and how it works. It takes in a 10-bit binary address. Now of course you can expand this to have more bits, but the larger you get, the laggier the instruction memory will be. So it takes in an n-bit address code over here, and it outputs our instruction, like the instruction stored at that address. So in this example we are selecting address 0, so this column will turn on, and the instructions stores in this column will go into the output of the instruction memory. That's basically it. Okay, I really hope that makes sense. You, like, as a REST owner, like, you don't really need to understand like all of the intricate details of how this thing works. You just need to understand the idea behind it and also how to use it. So to use it, you just have to input your desired address over here, and you are gonna get the instruction that you want. And the instructions are stored in one of these columns, in multiple columns like this. Each of the columns stores an instructions, and we can load in the instruction by replacing a block with like repeaters. So that's how you encode things. Of course there are automated tools for you to do this. Mattbatwings has that, but as of right now in his series, and I have asked him in the Discord server, he told me that the assembly only works with the finished build and not this, so I will not be using that just yet, but we will eventually after we finish our computer. We are currently at episode 5, so we are halfway there. So yeah, let's keep moving forward. Now because the instruction memory is gigantic, as you can see, even though this only it only contains like 1024 instructions here, is really big. So I will not gonna build this by hand, and instead I will just gonna copy paste this and place this instruction memory into our RESTful world, and then I'm gonna show you how to connect the instruction memory to the current computer parts that we have in our world. Alright, so I have put the instruction memory into our world, as you can see. However, this thing is so big that I honestly don't know where to put it. So I'm just gonna put it in the air, and I will gonna move this part up there later when we try to connect this thing with all of the stuff that we have done here. So how exactly can we connect both of these like parts together? Well, if we follow Mattbatwings diagram, we will understand exactly how to do this. And don't worry, I will gonna guide you through how to do this in Redstone Minecraft, so you can connect them yourself. Okay, before we start connecting, we need to label some numbers. So the bottom bit will be bit 0, and the top bit will be bit 15. Now the order of this cannot be changed because this thing is following Mattbatwings' encoding method, and we are also following his encoding method. So the order cannot be changed. Of course, if you are using a different encoding method, you can change to suit your situation, but for now we will gonna follow Mattbatwings' encoding method for simplicity's sake. So in the diagram we have bit 0 to 3 going to the right of the register. What I mean by that is the first 4-bit bottom bits of the instruction memory that will go into, like, those bits will go into the cyan lines over here. Then the next 4 bits will go into operands 2, so bit 4 to 7 will go into these 4 input bits, and then bits 8 to 11 will go into these 4 right here, and the final 4 bits will go into the operation code over here. And yeah, let's connect them like that, and we should be able to do some insane program. Alright, so I have connected the outputs and inputs of the control ROM plus the register file with the outputs of the instruction memory. So I have color coded all of them here. The lines are the control ROM, the blue lines are the two operands, and the cyan line are like the right or operand number 3, basically the right function of the register file. Now we have to add in some multiplexers, and if you don't know what a multiplexer is, it's essentially a circuit which allows us to select different things using the same circuit. So for example, in one condition it can go to A, and another condition it can go to B with the same input. So it's a pretty powerful circuit, and we kind of need that right now in the diagram because we have to override some stuff, and a multiplexer here is perfect for that. If you want to know more about multiplexer, just search up on the internet, or watch Mattbatwings Redstone Reloaded series about multiplexers. I will link all of that in the description for you to check it out. Okay, so I have added the two multiplexers. Here's one, and these multiplexers allow us to either select these 4 bits to go into the register file, or these 4 bits to go into the register file. These 4 bits are bit 0 to bit 3, and these 4 bits are from bit 8 to bit 11. So they are exactly the same as in Mattbatwings diagram. We also have another multiplexer over here. This one is a bit more spread out. That's because I have to snake all of the redstone around to fit in this tiny area, but it works. It still acts like a multiplexer. I have also added 2 new operations. So the first operation in opcode 0001, so opcode 1, is load immediate. Now this operation allows us to basically load in data into our register file fully automatically. So if you remember in the last episode, we have to do that manually. We have to load in data into the register file manually using these gray lines right here. But now with this load immediate function or operations, we can actually tell the instruction memory to load in data for us. We also have a no operation or no op, and this operation basically allows us to stop everything as of right now. So it disable the register file, and since the register file doesn't work, the ALU doesn't work as well, and so all of the instructions from the instruction memory will not go anywhere. Now I want to see if everything is wired correctly by testing out a program that I have written. Okay, so here is a small program that I have written using Mattbatwings assembly compiler. Here's basically how you write like assembly code in his compiler. I have learned a little bit so I can write this program. But basically what this program does is it first loads the number 4 into R1. This is the second instruction, and this instruction tells us that we need to load in number 5 into R2, and then this instruction add R1, R2, R3 basically means add R1 and R2 together. So we take R1 and we plus R2, and the result of R1 plus R2 will be stored in R3 or register number 3. And finally we have this operation, and this operation basically means stopping the program. So we haven't learned about this yet in the series, but this basically tells the compiler that hey, the program is done, you can stop. So yeah, basically now the expected result that we should get in R3 when this program finish running is R3 equals 9. So there should be a 9 stored in R3. Now if we run start, I want you to pay attention to the register window, and we should see that R1 has a number 4 in here, R2 has a number 5 in here, and R3 has a number 9. So that is exactly what's going on here. Now I will have to load this program into our instruction memory. So we have to put this inside of our instruction memory. But how the hell can we put this into like Minecraft? Well, we first have to translate the assembly code here into machine code. So how can we do this? Well, let's try to translate each one of these lines by hand. Okay, so let me try to do this. First we have LDI, R1 and 4, right? So if you have watched Mattbatwings video, you should be able to know how to do this, but if you don't, I will try to teach you here. So first we need to convert LDI. So the LDI is the operation code for LDI, and if you remember, the operation code for LDI is 0001. Next is R1. So R1 is register number 1, so the first operand will be 0001, and finally the next 8 bits will be number 4. So 1 2 3 4 5 here 6 7 8, and basically we can turn the assembly code here into machine code, and now we can load this machine code here into one of our instruction column in our instruction memory. We can do the same for LDI or 2 5. It is the exact same. So LDI, the machine code for it is 0001. Next is R2, so R2 is 0010, and finally we have number 5. So the next 8 bit will be number 5. So 1 2 3 4, and then 1 more 0, then 101. 101 is 5 in binary. Next is add R1 R2 R3. Add first let me write down the like the assembly code, and now we can turn it into machine code, and the machine code is first is add, and add operation code is 0010 0010, and then R1 is 0001, R2 is 0010, and R3 is 0011. And just like that, we have turned our program into like machine code. We don't have to do this yet because we don't have this operation yet in our computer, so we only need these 3. Now I'm gonna show you how to load these 3 like instruction into the instruction memory. by hand. Okay, now I will gonna show you how to encode the machine code here into our instruction memory. So first we're gonna start at address 0, and we just keep going like 1 up, so we just keep counting up. So 0 and then 1 and then 2 and then 3 and then 4 and so on and so forth. Okay, alright, now we will first gonna go to address 0, and we are gonna put in our first instruction. And the way we're gonna put the instruction in so that the order is correct is we go from left to right, and in the instruction memory that means going from top to bottom. Okay, so the first 4 bit is 0001. Okay, let's do that. So 0001. So we gonna replace that with a repeater. Then we go to the next 4 bits. So the next 4 bits is 0001. So again, the exact same 0001. Okay, we do this, and now we were gonna go to bit number 3 from the bottom up. So we go 0 0 0 0 0 and 001, which is not that one, it's this one, and we have 0 0 here and then 1. So that should be our first instruction. Now we were gonna go to register, or not register, but address number 1. So now we have to find address number 1, and this is address number 1 right here. Again, we do the same thing. We go to the top and we read the instruction from left to right. First is 0001. So 0001 is this one right here. Then we are gonna do 0010. Okay, so 0010. Okay, next we gonna go with 5, so 101 at the bottom. So we go to the bottom, 1 over here, then 0 and then 1 here. So that is our second instruction. Now we were gonna go to address number 2, and at address number 2, which is this one, we were gonna go to the top and we look at instruction number 3. So instruction number 3 tells us to first input 0010. Okay, so 0010. Next we're gonna add 0001. Okay, so from here 0001. Okay, next we're gonna input 0010. So 0010, and finally we have 0011. So 001 and 1. Okay, so in theory that should be our programs fully loaded into our instruction memory. Now what we need to do is very simple. We have to go from address 0, and then we hit the clock signal to activate the register, and then we go to register 1, and then we do the same. We hit the clock signal and then register number 2, and in theory we should have register number 1 with the number 4. So these 2 registers over here. Register number 2 will have number 9, or number 5, and register number 3 will have number 9. Okay, so let's try to do that. First, address 0. Okay, we have address 0. Now we were gonna press the clock signal, and in theory we should see a 4 in register number 1. And we should see register 0 doesn't have anything. Register 1 has number 4. Alright, so we have successfully loaded register number 4 into oh, not register number 4, but load in the number 4 into register number 1. Now we are gonna execute the second instruction. So we're gonna go here. Oh wait, no, that the second instruction is at address 1. Now we do the same, and in theory we should see number 5 in register number 2. So let's see here. This is register number 1. Let's check register number 0. Nothing. Okay. Register number 1 has number 4, and register number 2 has the number 5. Nice. Okay, and finally we're gonna execute our final instruction. Store at address 2 in the instruction memory, and we're gonna hit the clock signal, and we should see number 9 in register number 1, 2, 3, and we should see 1001, and that is 9 in binary. So we have successfully put a program into our instruction memory, and then execute the instruction memory, or not just execute the instruction memory, but the everything here as well. So that basically means that all of the things that I have wired here is correct, and we have successfully executed a program. All of the results are stored in the registers, and our program is stored inside of our instruction memory. Alright, so that is the end of today's episode. Overall, I have learned quite a lot in today's episode. I learned about instruction memory, I learned about assembly code, like how to actually write a piece of program in Mattbatwings assembly code. And I also learned quite a lot about how to follow a diagram, because today's diagram is actually much more difficult to follow than in like the previous episode, but I had a lot of fun, and I hope that you do as well. So wish you a very good luck that you managed to connect the current stuff that we have here with your instruction memory. And if you have a different design for instruction memory, let me know. You can share that on maybe like Mattbatwings Discord server. I will be sure to check that out as well. Yeah, that's the end of today's episode. Okay, thank you very much for watching, and I will see you all in the next video and episode of Learning Rest the Computer with Mattcraft. Have a nice day, everyone.